Hello, and welcome to part 3, covering section 3 from chapter 4 from the Cosmic Perspective, ninth edition. So this is the third video covering chapter 4. In this video, we're going to talk about the conservation laws in astronomy, all right, which are kind of like the conservation laws in physics, just applied to astronomy. Our goals for learning in this section are to answer the questions, why do objects move at constant velocity if no force acts on them, right? So we've heard that. That was one of Newton's laws, the first. What keeps a planet rotating and orbiting the sun, right? How does it continue to do that, right? Does it take extra energy? Where do objects get their energy, right? How do we even track it? Well, why do objects move at constant velocity if no force acts on them? Well, this is known as conservation of momentum. So this is the underlying idea in the guise or under the name of a conservation law. Now, really, this is the same statement as Newton's first law of motion, but it's really helpful to think about what things are conserved in nature, because not that many things are conserved. Velocity isn't, acceleration isn't, forces certainly aren't, but momentum is, which means that between any interaction, like a collision, or an explosion, or a gradual collapse of an intergalactic nebula, whatever it is, in all those processes, momentum is conserved. Now remember, momentum is defined as the product of mass and velocity. Okay, so for example, in an everyday terrestrial example of a ball colliding with another ball, the first ball has some initial non-zero momentum. The second ball at rest has zero momentum. Anything at rest has zero momentum because, after all, multiplying by zero gives you zero. Once they crash together, momentum is conserved, which can allow you to calculate the final velocity of the ball. Velocity is not conserved, but momentum is, and allows you to do things like predict what's going to happen after this collision. By the way, in this particular collision, it might look like velocity is conserved because it's the same value before and after, but that's only because the balls share mass. If they're different masses, velocity, you'll have different numbers before and after, but momentum you will not. So the total momentum of interacting objects cannot change unless an external force is acting on them. So why the caveat? Why the unless? Well, that's just because that means that over time, yes, if you put in a force, if you apply a force to a system, of course you can change its momentum. That's Newton's second law, okay? F equals ma. Change momentum is an acceleration, but that's an external force. If you look at the system and you make the system sufficiently big that there is no external force, or the only thing you care about is like a collision like this, where there's nothing outside of the collision, the momentum conservation is great and is accurate. Interacting objects exchange momentum through equal and opposite forces. So the actual event that happens is an event of reaction forces. But it might happen so fast that it's much easier to track the momentum before and after, rather than trying to figure out the forces during. Thought question number 4, fourth one in this chapter. A compact car and a large truck have a head-on collision. Are the following true or false? So you want to decide for each of the statements, true or false. Statement 1. The force of the car on the truck is equal and opposite to the force of the truck on the car. Okay? Statement 2. The momentum transferred from the truck to the car is equal and opposite to the momentum transferred from the car to the truck. Okay? Statement 3. The change of velocity of the car is the same as the change of velocity of the truck. So which of those are true? Which, if any, are false? All right? Well, we've got a true. That's Newton's third law, equal and opposite forces. For every force, there's an equal and opposite reaction force. And definitely momentum is conserved, okay? So whatever is the transfer of momentum from one to the other, it's the same, okay? Even though the truck is so much bigger, it still receives the same amount of momentum, or there's still the same amount of momentum transferred. But it's the velocity, you see, that is definitely not conserved, right? The truck might just barrel right through the car. The car might go from a forward velocity to a backwards velocity, right? So huge change in velocity for the car, marginal change for the much more massive truck. So that's conservation of momentum. Well, it turns out angular momentum, which is just rotational momentum, momentum of orbits and spinning around one's axes, well, that is also conserved. All right, so it's appropriate that they both have momentum in their name. Okay, so angular momentum, by the way, the actual official formula is mass times velocity times radius. Do you see the difference? It's just a little bit more complicated, and it only applies to rotation. So, for example, for orbit, right, if this is the sun, and we have the Earth orbiting the sun, not to scale, then you would have the mass of the Earth times the velocity of the Earth, and then multiplied by the radius of the orbit. Okay, so that would be the angular momentum of Earth's orbit. You could similarly find the angular momentum of Earth's rotation, but it would have, although the same value of mass, because it's still Earth, it would have a different velocity, because you'd want the velocity of a point along Earth's equator, and it would have a different radius, because it would be the radius of Earth rather than the radius of Earth's orbit around the sun. But both of them would have values of angular momentum, just different values. And both those quantities, orbital angular momentum and rotational angular momentum, are conserved. Okay, so the angular momentum of an object cannot change, see, just like we said for momentum, unless, so again, caveat, an external twisting force, which is known as a torque, as I called it before, a twisting force is a torque, is acting on it. All right, now just like we have this formula for angular momentum, and it looks a lot like the formula for momentum, but has this extra term multiplying by radius, it's actually really similar for torque. Torque represented usually as this, as a actual Greek letter called tau, which looks a lot like a curly T. So I kind of did my first T like that. But torque is equal to force times radius. So it's just like force with a radius tacked on. Okay, so really same idea as we see between momentum and angular momentum. Okay, so again, why the caveat with the external twisting force, the external torque? Because you can change angular momentum. Like you can even change the orbit of a planet, but you have to bring in an outside force. That doesn't typically happen. Once a solar system is developed, like our own solar system, there's not a lot of outside forces that just come in, right? We would have to have some sort of rogue planet or giant comet from another solar system enter and submit our planet or whatever part of our solar system to a large external force that wasn't there before. Okay, all the forces that exist in the solar system remain the same over millions of years. Okay, so Earth experiences no twisting force as it orbits the sun, so its rotation and orbit will continue indefinitely. Okay, there's no new external forces on the Earth. All right, makes sense, right? Okay, so what keeps a planet rotating and orbiting the sun, right? If there's no new forces on the Earth, and therefore its angular momentum of orbit, for example, doesn't change, how does it keep going, right? Why doesn't it gradually slow down over time, for example? All right. Well, the idea is that angular momentum is conserved. All right. So this means it will just keep going. If there's no, like I said, if there's no external force, it's just going to keep orbiting. It doesn't need any new energy. The energy associated with its orbit, which is getting ahead of ourselves a little bit because we'll talk about the conservation of energy soon. But in this case, the angular momentum of its orbit is just totally conserved. All right. Now, an application of that, more than just understanding that planets continue to orbit indefinitely, is that planets that have elliptical orbits slow down and speed up throughout their orbit, which is a really good example of conservation of angular momentum. So we see, interestingly, that this idea of planets going faster when they're closest to the sun and slower when they're furthest away is conservation of angular momentum, which also we have seen before in a previous chapter by another name. We saw it as Kepler's second law, all right? So it turns out that, and that did predate it. So Kepler's second law was the first time anyone published this idea. Later on, mathematicians and scientists were able to see that it wasn't its own unique law that just applied to planets, for example. It was, in fact, just one of many manifestations of conservation of angular momentum. Now, here's the idea. If we have a very dramatic elliptical orbit where there's a point where this orbiting body is much closer to the sun and another point where it's much further away, well, those very different values in radius are going to result in different values of velocity, because angular momentum is the product of the three: mass, velocity, and radius. So if your radius goes way down, then your velocity must go way up, because that product must remain the same because the mass hasn't changed and the angular momentum can't. You see it? All right, so as r goes up, v goes down, and vice versa. All right, so here r became really big, therefore v became small. All right, so they'll swap, right, indicating conservation of angular momentum. In this case, varying the radius and velocity terms that just happen naturally. Okay? Now, this same idea also applies to objects that change their shape, right? So not just elliptical orbits, but things that actually will pull in on themselves. We see that here with an ice skater. He pulls in his arms and they spin faster because their radius has decreased, okay? And not an orbital radius, but object size radius. So if the Earth was somehow to change its shape and not become a sphere, but instead become a more squished rod shape or something, then the planet would speed up, right? That'd be terrible, right? Although the changing shape would probably be worse. Now, but there are things that there are objects in space in astronomy that do change shape. It usually happens during the formation of something. As stars begin to form and they collapse in on themselves, becoming denser to the point that they begin having fusion and reach equilibrium. Well, during that collapse, that phase of becoming smaller, they speed up. Because they get smaller, they must speed up. That's conservation of angular momentum. And even before stars do that, they start off as a gas. So everything that became the star and the leftovers that became the planets in the solar system all started as a large, slowly rotating cloud of gas in space, some sort of nebula. And as it collapsed and condensed, it sped up much faster, leaving us with quick orbits that we see today, right? We even see it with the gas giants. The gas giants themselves formed from rotation within the own solar system. And that's why if we look at the rotation rates of the gas giants, they're quite quick. They have day lengths that are fast, like only 12 Earth hours, for example. So even though they're such large planets, Jupiter and Saturn being examples, all conservation of angular momentum. Things get smaller, they spin faster, okay? Usually a gradual process in astronomy. Okay, so there's another very important quantity, I already started talking about it, that's conserved in nature besides momentum and angular momentum, and that's energy. This is probably the most important, okay? So, what is energy? Well, let's do a little review here. Let's make sure we understand what energy is. Energy makes matter move, right? So energy is capable of moving things. You might say, well, isn't that what forces do? We were just talking about that, right? Forces change velocities. They take an object that was at rest and they give it a non-zero velocity, for example. They turn things, all that. That's true, right? That's absolutely true. Forces do work is the term, and then therefore forces can change energy. But sometimes we can not think about the forces, the exact interactions. Instead, we can just look at points in time. We can track things. We can say, okay, this is how much energy there is in this solar system this year. How much is there next year, right? So we can compare and find out where the energy went. So energy conservation is a way for us to understand motion and matter moving from one point to another, okay? So it's conserved. It allows us to track it. It can transfer from one form to another. It can also transfer from one object to another. So we have object transfer and form transfer. When we say form, there are many types of forms of energy. They're all related, but you can change, for example, the energy of motion into the energy of heat. You can change potential energy, which is like gravitational potential energy, having something lifted above the ground. It has the potential to fall. There's also electrical potential energy. So all of those can go from one to another, okay? Often many types of energy, many forms of energy are involved in just a single interaction. Okay, so here are the big types of energy, the basic types. Kinetic energy is the energy of motion. Radiative energy is the energy of light. Light is very unique from everything else. Potential energy is stored energy. That's why I talked about lifting something up, gravitational stored energy. You can also have elastic stored energy, like in a spring, right? So there's lots of examples of potential stored energy. There's even potential energy inside of atoms, like electrons have potential energy relative to the nucleus. Inside the nucleus, there's nuclear potential energy. So it's actually a very encompassing, expansive idea. Okay, so energy can change types, but can never be created or destroyed, right? So you can definitely shuffle around between kinetic, radiative, and potential, right? You can have these processes, and we see them in an environment, in an ecosystem like the planet. We see it, as energy goes into other planets, even ones that don't have life. We see interactions of energy. Energy gets absorbed by Venus, right? Where does that energy go? Why? It goes into the very, very hot atmosphere. It affects the rocks. The rocks become molten, right? We have flowing of energy from the sun into Venus. Then we have Venus radiating energy back into space, and so on. Okay, so there's always flows of energy flowing in time, tracking in time, and flowing in space from point A to point B. Okay, time one to time two, point A to point B. Okay, so let's talk a little bit more about the types of energy. Okay, so thermal energy, that's the energy of heat. Okay, it's a subtype of kinetic energy technically because it's basically chaotic motion. So when we think about kinetic energy, it's often motion that we can track in a very defined way. So we talk about the kinetic energy of, like in the picture, a bicyclist, because it's just that one solid bicyclist, right? We're not interested in the details of little parts of the bicyclist. We just treat them as one moving object. We do that with planets quite a bit. So we can talk about the kinetic energy of a planet as it orbits, kinetic energy of an asteroid or something, right? One solid object. But when we talk about the kinetic energy of a gas, there are trillions of individual particles all bouncing off of each other. So that type of kinetic energy is impossible to track or impractical to track on the individual particle level. So instead, we talk about it in a stochastic or probabilistic way, which is just mathematical speak, I guess, for just saying that we can generalize things, we can approximate them, we can come up with these distribution arguments and so on. Okay, well, suffice to say, it is the collective energy or collective kinetic energy of many particles, right? So you can have thermal energy of a rock, thermal energy of air, thermal energy of water. Thermal energy is related to temperature, but is not the same. They have different units, okay, fundamentally. Temperature is a measure of the average kinetic energy of the many particles in a substance. So we say that temperature, all right, temp, is proportional to the average kinetic energy, all right? So kinetic energy average. They're not equal, but there's a direct proportionality. Temperature has its own unique units. It's considered a base unit, and temperature has a base unit of Kelvin. Okay, let's talk about that. So the scale that we use in astronomy almost exclusively is the universal temperature scale Kelvin. We call it a universal scale because it has an absolute zero. Actually, we also call it an absolute scale. It is the only temperature scale where absolute zero is part of the scale. This is a theoretical value where all motion stops. So where a gas would just have no leftover kinetic energy. I say it's theoretical because it actually, as far as we know, takes an infinite amount of energy to make something completely come to rest. You have to pump that much energy out of it. But we can get things close to absolute zero. For some perspective on what Kelvin looks like, room temperature, right, is about 293 Kelvin. So that's kind of like 60 degrees, right? So that'd be 293 Kelvin. Freezing water, so the temperature at which water freezes, at least at sea level on Earth, because water will freeze under different pressure conditions at different temperatures. But on Earth, water freezes at about 0 degrees Celsius, and that corresponds to 273 Kelvin. Don't worry about the 0.15, just 273 is good. As far as how that relates to the temperature scale that you're probably most familiar with, Fahrenheit, well, 0 is 32, because again, that's freezing. So you could then think of 32 Fahrenheit as 273 Kelvin, right? By the way, boiling water is going to happen up here. So at 100 degrees Celsius, which is 373 Kelvin, okay? So we need to be able to convert over from Fahrenheit to Celsius to Kelvin, but really our goal is to exclusively work in Kelvin. So thermal energy is a measure of the total kinetic energy of all the particles in a substance, right? So temperature is related to some average particle, but if we want to quantify the energy, it's the sum. We total it up. All right, so that means that it depends on both temperature and density, because the more dense substance is going to have more particles, so that it can have a bigger sum. All right, so for example, we can have a certain amount of energy in water, right, when it is at a temperature of 212 Fahrenheit or 100 degrees Celsius, and that energy might be greater than the amount of energy in the much hotter microwave, because there's just fewer particles in the low density air in the microwave than the much higher density water. Okay, so that's a little bit about thermal energy, a subcategory of kinetic. But what about gravitational potential, right? Because that's one of the potential energies. As I said, it's a very important idea, okay? Potential energy, stored energy, okay? So gravitational potential energy is the energy on Earth that depends on an object's mass, gravitational acceleration. That's the part that makes it unique to Earth. Because remember, on Earth, gravitational acceleration is 9.80 meters per second squared, but it's not that number at all on other planets, okay? Unless you found a planet that was the exact size and density of Earth, okay? And the other thing that the gravitational potential energy depends on is H. Now, what the actual formula looks like here for gravitational potential energy is actually pretty straightforward. We say that potential energy, gravity, so little g for gravity, is just mgh, okay? So as long as you're on the surface of a world and you know g, or you're on Earth and you know that g is 9.8 meters per second squared, then you just multiply that by the mass of the object in kilograms and the height of that object above the ground in meters. Now, obviously, potential energy is relative, right? Because the height above the ground might be the ground of the floor of the room that you're in. But then if you look out the window, you realize you're on the fourth floor. So the ground is actually much lower than the first way you calculated. So which potential energy is right? Well, they both are, right? So there's no one potential energy. Potential energy is what you care about, right? So if you care about the potential energy relative to your floor, then that's the one you use. But if you're going to be dropping something out of the window, then you'll use the potential energy relative to the ground 4 floors below. Okay, so in space, things are a bit different involving gravitational potential energy. There's not one value of little g, for example. There's not one value of acceleration. Instead, you have to consider gravity in a more fundamental matter. So in space, an object or gas cloud has more gravitational energy when it's spread out. So anything spread out has gravitational potential energy. Why? Because it has the potential of collapsing. It has the potential of becoming more dense as everything is tugged into the middle, because all matter is going to pull on all other matter. But we'll talk about that more when we talk about the universal law of gravitation. So in other words, we have energy being conserved as the cloud collapses, as the gravitational potential energy gets converted to something else. Okay, so it's got a lot of gravitational energy to begin with. Where does that energy go, though? Well, it's going to go into thermal energy. It's going to go into chaotic motion, a chaotic form of kinetic energy. So we're going to have thermal energy being created by the conversion of gravitational potential energy into it. Okay, energy as a sum of all types of energy is conserved, but we have a change from one type to another. All right, so a contracting cloud converts gravitational potential energy to thermal energy, a very common and important process in astronomy. Stars and solar systems are formed this way. And even galaxies, especially in the primordial universe, when people look astronomers look very far away, tens of billions of light years away, and they see that the early, because they're looking tens of billions of years into the past, and they see the early universe where galaxies were first being born, they see giant intergalactic clouds, proto-galactic clouds, proto being before, collapsing into galaxies and forming them under these same principles. Now, there is almost a caveat here, something that we've been ignoring or sweeping under the rug, and that's the fact that energy is conserved as long as you come to the amazing conclusion that was just discovered in the 20th century that energy and mass are actually the same thing. Because it turns out that there's really no difference. Mass is just a form of nuclear potential energy and a little bit of also electromagnetic potential energy. Really, everything that makes mass, that holds the protons and neutrons together inside of the nuclei of all the atoms on the periodic table, everything that makes atoms be able to hold on to electrons, or the nuclei be able to hold on electrons, and those electrons interact to make all the molecules that make our biological world possible, as well as make all the known chemicals of the universe. Well, all of that is just potential energy. So there's nothing like that makes mass just purely mass, right? We know that mass has these properties like inertia, right? There's definitely absolute rules that it follows, but it can be converted into just energy. You can take mass and lose some of it during, especially nuclear processes, and what you get is either extra kinetic energy or extra radiative energy. And that amazing relationship that mass can become energy and energy can become mass, therefore they're just two sides of the same thing, is represented in part of Einstein's special theory of relativity that says E equals mc. Okay, so mass itself is a form of potential energy. All right, so, and by the way, the formula, if you look at the numbers, make it very clear that a small amount of mass can release a huge amount of energy, which you probably are familiar with because that's what makes hydrogen bombs possible. That's what makes the huge amount of energy released by stars possible, right? So concentrated energy can spontaneously turn into particles as well. So you can actually go the other way. It's not just mass becoming energy. You can actually create mass from energy. All right, that's pretty cool because we have to be able to show it goes both ways. Practically speaking, that's hard to do, right? We only do it in very high energy labs here on Earth. It does happen naturally in space as well. But point being that it goes both ways. All right, so that's the idea. E equals mc squared tells us that mass is itself another form of energy, fitting in as a puzzle piece of the big idea that energy is conserved. Okay, so energy, right? Always conserved, conservation of energy. It can never be created or destroyed. Okay, you can turn into mass, you can turn mass into it, you can change kinetic energy into thermal energy, potential and the kinetic, all of that, but it can never be created or destroyed. Okay, it can just change between forms and objects. The total energy of any system is always the same. When we say isolated, that's just, like it's a system that doesn't interact with any other systems, because otherwise that other system might be giving it energy, and then it might not seem conserved because there's energy coming in from that side. So what's an isolated system where we can be sure nothing is coming in from that side? The universe as a whole. So everything that was created in the Big Bang, everything that we know as the universe, that system, that huge system, must have conservation of energy. So, what have we learned in conclusion from this section? Well, we've learned that momentum is conserved, and we've also learned that angular momentum is conserved. And to wrap things up, we learned that energy is conserved and has three types: kinetic, potential, and radiative. We talked the least about radiative, but that's because we have a whole chapter for it, so wait till chapter 5. And we learned that, amazingly enough, mass itself is just a very special form of potential energy. Okay, so let's go ahead and in the next video talk about the universal law of gravitation, which I've hinted at a lot in these first 3 videos, and it'll be nice to finally see what I'm talking about, because this is the law that makes it possible for us to say that all matter is attracted to all other matter. Well, so I hope you'll check that video out, and I hope you found this video on section 3 interesting and informative. Thank you so much for watching.